So I think there's lots of ideas that any language can take that Julia's, I think, accidentally done very well. So to get started, so Julia created 2012 by these fine folk, targeting scientific computing. A couple of years ago we had the 1.0 release, which was we got stability, things stopped breaking, everything got very boring because your code didn't just break the next day, it just worked. So my employer runs Julia in production. Julia is stable enough that we can do like a very large production system that we need to have high reliability on. So that's kind of what 1.0 gave us. So on to the main topic of this talk. What do I mean by composable? So I said before that Julia code is, what's the time I talk, is very composable, and I want to explain kind of why I think this happened. So here's some examples. So if I've got some type that represents a scale or a number, I'm going to attach some metadata to that type, like measurement error. Then I should be able to just do that to my scalar. I shouldn't then have to go and implement array code, because that'd be silly. This is a property of the scalar, not of the array code, so those should be completely independent. Some of the latest work in machine learning is on these differential neural ODEs. And so if you build a differential equation solver, a well-established piece of scientific software, and you build a machine learning library, you should use those together. You shouldn't go and rebuild your differential equation solver inside your machine learning library, because again, why would you do that? That would be just a massive waste of effort. And perhaps another example is if I built something to give my arrays some metadata, like some name saying that the first dimension is time, the second dimension is location, and then I build another package that says this array runs on the GPU so it can go fast, I should be able to use those together as like two separate packages, and it should just work. So that's what I mean by composable. You've taken separate things and then used them together, which is the way things always should work, and it's the way it can work. But it often just doesn't work that way. But we find in Julia it works that way more often than I think one would naturally expect. So I'm going to suggest a few things that are counterintuitive. I'm going to say that not only is it because Julia has some great features, which I'm definitely going to talk about, but also because a few features are missing or just not that powerful that has kind of caused other things to end up working better. Or at least allowed for some of the great features to carry their weight. So I'm going to talk about things like the namespace pollution is kind of common. The convention is to pollute your namespace in Julia, which is weird. No one ever got around to make it easy to use like local modules. The type system can't check correctness. So if you've got a static languages background, like I used to have, it'd be like, what, is this even a type system? It can't even tell me like what my function is going to return. But then it gets counteracted by conventions around communication, being able to create packages very easily, and being able to use duck typing and model dispatch together. So get right into it. So Julia namespace pollution is the convention. So in many languages they'll say, we're going to use a package foo, and we're going to use like method A and B and C from it. Whereas in Julia, the standard thing, not the only thing, but the standard thing to do is say, I'm going to use package foo, and I'm going to take everything the author has said is exported. The whole public API, put it in my namespace, just give me access to it, which sounds silly to me. But turns out that this works, or at least it gives you advantages, indirect advantages, but it obviously gives you problems. So if we've got some package called bar, and it defines a method called predict for its bar model. Another package foo defines predict for its foo model. Then I write some code that eventually calls predict on these models. Then what's going to happen? Which predict is it going to use? The answer is it's just going to throw an error because it's like, I don't know which predict, like you imported them both, and so it's completely ambiguous. So you can tell it it's used. You can say, well, in this one I want to call the one from bar, and this one I want to call the one from foo, and that'd work. But the package author could also solve it. So if rather than defining their own unique name predict, they overloaded a name from another namespace, say statspace.predict, then instead all your use of predict in this code will be statspace.predict hitting the overload defined by each of the packages. And so what does this do to a community? From a community perspective, people come together and they think, well, I want to use my package and I want to use someone else's package, but if I don't have this like common package together that establishes a convention, establishes some names of which I'm going to overload, then the user's going to have to keep writing all this extra code to like pick which one to use. And so to do this, it's basically just encourage people to come together and like talk about what the API should be and how things should be done. It makes people think about others. So the second one, again, kind of around namespaces. In lots of languages, it's very easy to like create a file and then you're like using this file and it loads it up as a namespace, it's a module, it's all very good. In Julia, that's actually really fiddly. Like people are saying, oh, we should remake that easy for ages, but I actually think we shouldn't. Because while using these like local files and modules is hard, creating a package in Julia is trivial. So if you create a local module, what are you getting? You're getting your namespaces. You get to feel like, oh, I'm a good software engineer. I'm not just writing these little scripts. This is a proper like module. It's got namespacing. And then later, you could turn it into a package if you wanted. But if we just went straight to a package, what do we get? We get like the standard directory structure. You could have your source, you could have your tests. We've got managed dependencies, so you know what's compatible with your package. So that all works. You can redistribute it. So obviously, no one's reusing code that you never redistribute. You can test it with the package manager's built-in testing system. And if you follow the recommended way, which is a second line, doing all that is like one line, use second line, you'll also get your continuous integration set up, you get your code coverage set up, you get your documentation set up. You get a bunch of like all the things which you should always have is all set up for you, and it's been made really easy. And so why would we stop and like spend our time making these little local modules when we could be making packages just as easily and end up with all these other benefits? I should mention, testing Julia code is really important. Since the JIT compiler, just in time, you don't even get your compile time errors until runtime. They are compile time errors, but they're arriving like non-to you testers, so that's like not great. So you just got to have your tests. And since the dynamic language, you don't get as broad a like family of compile time errors in the first place. So yeah, that's why I think that creating these packages has kind of counteracted some of the other downsides of Julia, because not having these things gets fixed up if you make sure you've also got really good tests already going. But onto like the main thing which Julia did right is, in my opinion, is having multiple dispatch and duck typing. So one of the main common advantages of dynamic languages is you can use duck typing. Not all dynamic languages that use duck typing. Some, yeah. These things are not directly tied, but it's very common for duck typing and dynamic language to be used together. And Julia uses multiple dispatch. It's kind of its thing. Like all methods are multi-methods. It's not like an obscure feature. It's the only feature. The other thing that kind of goes with this is open classes. I'm not going to talk about those today, but some languages you just can't add methods to things. Java's one. But yeah, multiple dispatch. So we're going to think about some library, the ducks library. Someone else wrote this library, and it's for doing ducks. So it's got a type called duck. It's going to find some methods on it. It's going to be able to walk, it's going to be able to talk, and it's going to be able to raise its young. So this is a duck, lovely library. And let's say I wrote some code. I want to simulate a farm. So in my farm, I'm going to take a list of adult animals, a list of baby animals. I'm going to make all the adult animals walk and talk, and then I'm going to pick the first of my adult animals. I'm going to say, this is the parent, and I'm going to have it raise all my baby animals. So this is like reasonable code for someone who wants to simulate a farm. And here's what happens. So I had 3 ducks and 2 baby ducks. It goes waddle, quack, waddle, quack, waddle, quack, lead it to water, lead it to water. Great, this is what I wanted to happen. So I could use someone else's library, which is good. But now I want to add my own extension. I want to have a swan. So I've defined my type, it's a swan. And I'm going to, let's try it out to swan. So I've got a swan, waddle, quack. Swans don't go quack. So what have we got wrong? We did some duck typing. It walked like a duck, it waddled, but it didn't talk like a duck because it did talk like a duck, and that was a problem because swans don't quack. So we can use single dispatch to solve this. So we're going to say talk, if I'm a swan, is to hiss. And I can try it out. Waddle, hiss. Good. This is what I want, single dispatch. We've had that for a while. So let's give this another try. So 3 adult swans, 2 baby swans. Waddle, hiss, waddle, hiss, waddle, hiss. Lead to water, lead to water. Now, if you know things about swans, swans do not lead their young to water. They actually carry them, and it's absolutely adorable. So we need to do this again. So we're going to redefine raise young. If I'm a swan, my child's a swan, I'm going to carry it on my back. So try it again. Waddle, hiss, waddle, hiss, waddle, hiss. Carry it on my back, carry it on my back. All is well in the world. Now I have a farm that has swans. Okay, so, but what if I want mixed poultry? So let's say I have 2 ducks, 1 swan, and 2 baby swans. So let's try it out. Waddle, quack, waddle, hiss, lead to water, lead to water. Now, again, if you know anything about ducks, you will know that ducks do not, in fact, raise swans at all. But yet we've hit the method for ducks. So it's acted like I was having a duck raising a duck, which would be to lead it to water. But that's not what's going to happen. If we gave a duck a swan to raise, a baby swan, it's just going to abandon it. So how can we achieve this lofty goal of having the duck abandon our baby swan? So we could rewrite the duck code. So we're going to check, is my child a swan? If so, abandon it. Otherwise, fall back to the default behavior of leading it to water. So this is an option. This will let you make it work. But it's got some problems. So I didn't write the ducks library. This is someone else's code. And if I want to like push them edit their code, then they're going to be like, oh, do I want to maintain this code about swans? Like I'm in a ducks library. It could be a lot of work. And if someone else is like, oh, but I want to add chickens and geese, they're going to be like, this is so much code. Look, all I wanted to do was ducks. Like, you're just putting all this work on me. So I could fork their code, but then I've just given up on all code reuse. Like they improve their ducks and I don't get any benefits from it. I could also use monkey patching if your language supports that, where I'll basically just overwrite their ducks method with my new method, and I can make it work. However, it has the downside that now, if they want to update it, I have to update my code too. So I've like lost all encapsulation. I have to know what code was inside their source to make sure things stay compatible. And if someone else does the same thing that adds, say, chickens, there's just no way. 2 monkey patches are going to collide and the whole thing's going to just crash. So that's not great. Try again. We could inherit from the duck. Dual inheritance doesn't work this way, but let's pretend it did. So adding a new type. This is duck with swan support, subtype of duck. So if I am a duck with swan support, I'll check if it's a swan. Otherwise, I'll cast myself back up to the duck type, and I'll do whatever the default is there, which was to lead to water. So this is an option. We can do that, but it has problems. Now I need to replace every single duck in my code base with something that is a duck with swan support instead. And if I'm using some packages, say extra duck utils that might return ducks, then I now have to like deal with the fact that they're going to return the wrong type. So that's like fiddly. You can engineer around it, but it's fiddly, and it still doesn't scale. If someone else makes duck with chicken support, and I want to support both of these things, what am I going to do? Inherit from both of them? Like, that's multiple inheritance. This is the worst kind of multiple inheritance problem. Like, we need to actually hit both methods. And it's really hard to resolve. Like, if you even have multiple inheritance in your language, then this is like the awkward case that doesn't do very easily. So we may end up writing a bunch of code to make it work. So that's kind of sad also. Or option 3, multiple dispatch. So I'm going to find a method, raise young, my parent type, if that's a duck, and my child type, if that's a swan, I'm going to abandon it. So this, very short, independent, I can write it inside my farm code. It doesn't need to like edit the duck code. If you're familiar with like sum types and pattern matching, this might look kind of familiar. It is kind of familiar. It's serving some similar goals of like recognize these 2 cases. It's a bit different because our sum type isn't closed in that a duck and a swan are actually just 2 independent types. They're not like joined together, so I can add more and more of these completely separately. But yeah, so model dispatch just lets us dispatch on not just type of the first argument, but on all the arguments. If I try that one, waddle quack, waddle hiss, abandon, abandon. Yay. So yeah, I have successfully got my baby swans abandoned, which was my goal. And I didn't have to add anyone else's code. I didn't have to go and like massively replace all my types. I just added like one method that's no longer than the original one. So we're now going to take a short break. Where I'm from, this is what swans look like. And we're back. So, does this happen in the wild? It's still nice to say theoretically have multiple dispatch, but if no one needs multiple dispatch, why have you added this to your language? Now it turns out in scientific computing, Julia's main use case, happens all the time. And I suspect in general it happens far more often than we're aware of, and we just kind of ignore it and don't worry too much because, well, we don't think of it as an option. I suspect one of the other main cases to do with like printing. If I'd like to render this for this particular type of I/O, say HTML, and this particular input, say a duck, and I want to render it differently for, say, a swan and Markdown, I think we also need to basically use multiple dispatch to be able to add more formats and add more types at the same time cleanly. But anyway, the main use case is really apparent though, is matrix math, which very common side of computing. So BLAS is kind of probably the most important library or API for scientific computing. It does linear algebra. So it does matrix multiplication and vector multiplication. You need it for like all of your machine learning and all of your scientific computing, all your modeling. It's very useful. So if you open up BLAS, it has like a giant pile of methods. It has this one, and they've all got these really kind of arcane 5-letter names. We have the first one, which is like, this is how you multiply two matrices. This is how you multiply a symmetric matrix with a matrix. This is how you multiply a complex Hermitian banded matrix with a vector. So we can see that we're kind of worrying about like, is one argument a matrix, is one argument a vector, is one symmetric? But we haven't encoded it into our dispatch system. All we've done is like just created this giant pile of methods you have to like look up manually, which works great for BLAS. Like BLAS has been around since forever, so. But it turns out people keep wanting to make more and more matrix types. So you can't just say, yes, I have done all the matrix types, because they keep making more. So this is a block array, which turns out to be really useful, where all of your arrays are in fact composed of other arrays, some of which might be like aliases for each other, so it can be very efficient. This one is a banded matrix, so it's all zeros except for on this diagonal band. This one is a block banded matrix. So all of my things are zero except for this band of blocks. And this one is a banded block banded matrix, where all my things are zero except for the blocks, and those blocks themselves are banded. I saw this one, I'm like, what? What is this even for? Turns out it really matters for partial differential equations. And if you have it, you can make things like easily 4 times faster, which matters if your thing was taking like months. And so people just keep on creating more and more matrix types, and we've got to let them do that. And multiple dispatch is kind of the elegant way to do it. More matrix types. So we also want matrix types for running things with GPU. We want to do matrix types that track what happened to it so that it can write auto-diff and like find your derivatives so you can do, say, ML. We want to like name a dimension so that we can be like, I gave this example before, like sum over all times. We want to distribute them over a cluster. And maybe we want to do like all of the above, including all the types. So like we need lots of matrix types. And that's why we need to be thinking about ways that let you have different combinations of different matrix types. And it feels really wrong to not generalize that, I guess. So a particular example I've mentioned before, these neural differential equations. So machine learning research has been going kind of on and off for about 20, 30 years, depending where you want to cut it. Has invented all these great types, great ideas. Differential equations, so solving differential equations has been going on for, I think, centuries. Like, they've been working out how to do this since before we had computers, and like the earliest computers have been building like systems for solving these. So we need all these types, and we need them all to work together. And that means we like definitely do need these ability to like combine these different systems, and we need to make sure that like they can communicate. So if I've got some one hot vector and I've got some banded block banded matrix, I better be able to multiply them. Like that's just important. So this is kind of my rebuttal to a claim which some people says, which is like, we have implemented all the matrix types, we're done. You have not implemented all the matrix types. Yeah. So kind of think a bit more about this lead on from the price point. So we've got this notion in general of a tracing JIT. Roughly what happens, you've detected some important case happening in the code, and you've worked out how to compile a specialized method that handles that case, and it's faster. Julia doesn't really have a tracing JIT. Julia has just a JIT. So Julia decides to specialize everything on all the types of its arguments. So every argument type you get, we're going to always specialize it, which is actually a pretty good approach. So it makes sense that the types are going to be very significant, and we're probably going to be able to optimize something that's of a particular type. So specializing everything types is probably a good idea. But then modal dispatch is on top of and beyond the JIT. So just specialization types will get you a long way. You'll hit better methods in terms of things like your code gen, what LLVM stuff you hit. You can eliminate some branches and that kind of thing. But modal dispatch lets a human go in and say, actually, you can use this totally different algorithm. And that's great. So back onto me, matrices. I like matrices almost as much as I like ducks. So if we've got two dense matrices, if you want to think back to the last time you did matrix math, that's where you have to multiply these by, take the rows, multiply them by the columns, sum them up. You're going to pay into this order 3 operation because you have to go through 3 different matrix dimensions. But if one of those matrices is diagonal, so everything's 0 except for on the diagonal, then all we need to do is go through the diagonal and we just scale up the rows or the columns, depending on which order we're doing it, by that, which means we only need to order 2 operations, because we only need to really go through 1 matrix, approximately. But if one of them is 1 hot, so everything is 0 except for 1 element, then we don't even need to do that. We find the 1 element that's non-zero, which we can directly encode in our type, and then we can just cut a slice out of the matrix. We can do indexing, and indexing is an order n operation. You just need the length of the row you've indexed out. So that's great. And if the extreme case, if one of them is the identity matrix, then you don't need to do anything because the identity matrix never changes the thing it's multiplied with. So you can just return the other input. So this kind of ability to insert a different algorithm based on the types is kind of the performance implications of modal dispatch. And I think it's quite compelling there. Another point is, anyone can have fast array processing if you're using standard types by either using BLAS, it's very well made, or throw in a GPU, which have very good BLAS and it's very good hardware for solving these problems. But not everyone has array types that are parametric on their scalar types, and the ability to be equally fast in both. So I mentioned the measurements example right at the start, where we've got this metadata attached to my scalar types, says how to propagate errors in terms of accuracy errors through the code base. There exist measurement libraries in the wild which have implemented this for their scalar type, and then we're well, now I need to implement this giant matrix API because I don't have the ability to have fast scalars in the same space as my fast arrays, so I need to have it entirely implemented, specialized for what's going to happen when I hit an array. And that's terrible. That's not fun. Why am I writing all this array code? I know about measurement errors. I might be a scientist who literally only knows about measurement errors, but it's fairly easy to specify for scalars. And there's lots more scalar types you want. So dual numbers perform automatic differentiation because of how they propagate through a system, and it's like a complex number, except for instead of square root of a negative 1, you've got square root of 0, but it's not 0, but anyway. Or you can throw in a symbolic type, which looks something like what Mathematica would do, where it would be able to manipulate equations, and then you can do kind of some symbolic algebra on your existing matrix types, if you can make them both fast. So we want all these things to work, and we don't want to have to touch the array code, except for maybe at the end we can do some careful stuff like BLAS does about checking about your CPU, cache sizes, and that. But most of the time you don't need it. We just want to implement these scalars. So having a type system that is parametric and the ability to kind of specialize in both gives us the ability to do the extremely specialized version, or the ability to just worry about the 2 parts one at a time. I think that's quite important. So this kind of brings me to the end of my talk. So I think people need to keep inventing new languages. I think it's good for the world right now to be inventing new languages. It's good for me, because I get to have new languages to use. I'd just like to request that when you are inventing your new languages, think maybe you should have modal dispatch. Make sure you don't not have open classes. Do not choose to have bad things. Like closing your classes is without very many advantages other than it looks pretty. Make sure your array types parametrically scalar types, and build your package manager in and have everyone using your package manager, and make sure you think about semver and all this stuff so that like stuff gets reproduced when you don't have pains to try to get your code to run on other computers. That's about it. Yeah, come talk to me. I have exactly 3 Julia stickers because I ran out. Also, ask me about Dex. It's a language from the standard ML family that doesn't support recursion or if statements. And it's like 3 months old. Yeah, I can take questions.